Okay, so today we will consider Bell states, which are arguably the most important states in quantum physics, in quantum computing. So, and they are important. You can say that they are very important because there are many names for them. Bell states, Bell pairs, EPR pairs. So these are all synonyms for Bell states. So Bell states, they are maximally entangled states of two qubits. We take two qubits, like we studied last time what are entangled states. They are very unusual, non-classical states. You measure one qubit, and state of the second changes. So Bell states are states in which this entanglement is maximum possible between two qubits. So they have, so there are several, there are four states which are called Bell states. Okay, so, but they all have very similar properties. Okay, and these properties are quite unusual, something which is not possible for classical objects. Okay, and Bell states, they are very, they use basically everywhere. So we will study, like in a couple of lectures, we will study quantum teleportation, which is one of the most interesting applications of this quantum physics. And this quantum teleportation requires use of Bell pairs or Bell states. So we can call, like informally, that we can say that Bell states are quanta of entanglement. So they are maximally entangled, like in the simplest, and in a certain sense, simplest entangled states. So we will start with considering one of Bell states, phi plus, in detail. Other Bell states, they have very similar properties. So what is a Bell state phi plus? Phi plus is a state of two qubits like this. So this is superposition of two computational basis states, of state 0, 0, so when two qubits has 0 or spin down, and 1, 1. This is superposition with equal weights. So there is no preference to 0, 0 or 0, 1. You see, there is weights 1 over square root of 2. Okay. So this is a state in which two qubits are simultaneously in state 0 and simultaneously in state 1. So this is a state that not possible to understand classically. We do not have classical analogs of such states. And well, when you work with them, you may get a feeling what this state represents and what you can do with them. So let's consider some simple things that we can do with this state. Let's start with single qubit measurement. So what would happen if I have this Bell state and I measure qubit 0, so this qubit, and say I measure it in Z basis, of computational basis. So what would be the probabilities of outcomes, and what will be the state of the other qubit, unmeasured qubit, if I perform such measurement? Well, this state is written in computational basis. So the answer is very simple. Like, we may get either outcome 0 or outcome 1. Probability of this outcome is just the square of this coefficient. So probability of 0, 1/2, probability of 1, 1/2. What would be the state of the other qubit when we get certain outcomes? So if I get outcome 0, measuring qubit Q0, the other qubit also in state 0. If I get outcome 1, the other qubit is also in state 1. So what we have here, when we perform measurement in Z basis, then I have two possible outcome of measurements. Their probabilities are equal, 50 by 50. And for these two different outcomes of measurement, my qubit that I not measured, as the other qubit, not measured qubit, ends up in the same state as the qubit which is measured. So there is 100% correlations between states of the two qubits. So what we see from measurement in Z basis, so this is that probability of getting 0, 1, and 1 is exactly 1/2. That means that measurement of this qubit does not give us any information. This is coin toss. It's not like we have qubit in a particular state, we measure it and we see, okay, here is some high probability of state 0, and low probability of state 1. Here it's coin toss, it's 50 by 50. So by itself, measuring this qubit in state Z and just getting this 0 and 1 does not tell me anything about this qubit. Okay, because this 0 and 1 is not, I would say, it's not intrinsic property of a qubit. This is something that we achieve during measurement. So the same as you toss a coin and say it falls heads up. It does mean that the coin was head up. This is something which is created by measurement. The same is here. At the same time, we have perfect correlations between qubits that we did measure and qubits that we did not measure. So by measuring one qubit, qubit Q0, I don't learn anything new about this qubit. But what I learn about other qubit. What would be the outcome of measurement of other qubit? Okay, so that shows that this Z projection, because we measure it in Z basis, Z projection of this qubit does not carry any information. But there is correlation between qubit states. So when we measure, we get information about correlation, not the qubit states. Okay, so this is what we have when we perform measurement in Z basis. But we can also perform other measurements. So we can perform measurement in any basis we want. What if we measure qubit in X basis? So let's do some math here. So let's calculate. So let's find what would be the probability of when we measure in X basis. There are two outcomes, either plus or minus. Let's consider outcome plus. What would be the probability of outcome plus, and what would be the post-measurement state of the other qubit? So how we can do this? Well, so here I measure only one qubit Q0. So I need to take scalar product of my state with partial scalar product with this outcome of this partial measurements. So outcome will be plus only with 0 qubit. And I need to find scalar product partial scalar product of this single qubit state with state of my qubit. So what is a state plus? State plus is a combination of states 0 and 1. And I take scalar product with 5 plus states, state 0, 0 plus 1, 1. So when I take scalar product of this term, it pairs with this 0. So 0, 0 is scalar product 1, 0, 1 is scalar product 0. And this part, it pairs with this state 1. So what I will have as a result? So here, from scalar product, I have 1. I have remaining state 0 of the qubit that I did not measure, and I have 1 over square root of 2 terms, factors. Okay, so this is from this term. From such scalar product, I have very similar combination, but with state of the unmeasured qubit 1. Okay. Now I can rearrange this term. So I can pull 1 over square root of 2 factor as a common factor. And what I have inside, 1 over square root of 2 state 0 of the first qubit. And here, 1 over square root of 2 state 1 of the first qubit. And what is this state? 0 plus 1. This is the state plus. The same as here. 0 plus 1, so it's equal superposition. This 1 over square root of 2 comes from normalization. So the result can be written simply as 1 over square root of 2 state plus of the qubit 1. So what this formula tells me, this spatial scalar product, this formula tells me that first of all, here is the state of the qubit. So the state of the qubit that we did not measure will be plus. So we measure qubit 0 in x basis, and we got outcome plus. So all these calculations are for outcome plus. Then qubit 1, qubits that we did not measure, also end up in the state plus, in the same state as qubit 0. This is normalization factor. So square of this normalization factor gives me probability of this outcome. So what is the probability that I will get outcome plus? It's a square of this, which is 50%. So we have exactly the same situation as for measurement in Z basis. So when we measure one qubit, well, and it's clear it does matter, it's symmetric, so it does matter which qubit we measure. When we measure one qubit in X basis, we can get plus or minus with equal probability. And the other qubit that we did not measure, ends up after such measurement in exactly the same state as qubits that we measured. So again, we see this situation that measurement of qubit does not give me any information about this qubit. It's coin toss, it's 50%. But once I measured one qubit, I know what would be the outcome of the measurement of the second qubit. There is a perfect correlation. And actually, it does matter that this post-measurement state of this qubit 1 is exactly the same as state of the qubit that we measured. What measured is that for this two outcome of measurement, the other qubit ends up in orthogonal states. So I can always distinguish them. So suppose we share a bell pair. You perform measurement of this bell pair, say in X basis, and you don't want to tell me the outcome. Say, I will not tell you. It's a secret. If I have the other qubit of the bell pair, I can perform measurement in X basis, and I will 100% of time, I can tell what was the result of your measurement. That works in Z basis, and that was in X basis. But that also works in absolutely any basis. So you can perform measurement of one qubit in bell pair in any basis you want. You will get two outcomes. And the other qubit, post-measurement state of the other qubit for these two different outcomes, will be some orthogonal states. They will not always be the same states as the state of the qubit that you measure. So if outcome of measurement is this state of the C0 and C1, well, they depend on the axis along which you perform measurement. So for Z, this is you can get either 0 and 1. For X, you can get plus or minus. But in general case of this C0 and C1, they depend on the choice of axis, on the choice of measurement. And there are like two different outcomes. So, but if you get outcomes like this, the second qubit will end up in the state that looks like a conjugated state with conjugated. With conjugated parameters. So on the Bloch sphere, this conjugated state is the state symmetrical with respect to y plane. So like if this is a Bloch sphere, and this is plane y equals 0, so one state is here, another state is symmetrical with respect to this plane. So they are not always the same, but they are like always 100% correlation. We get, and if I know in which basis you performed measurement, absolutely any axis, you tell me like, I perform measurement in such basis, that and I perform measurement in conjugated basis, and I can know for sure 100% of time what was the outcome of your measurement. Doesn't matter which measurement we have. So, yes?
So if I understand correctly, it's always the conjugated state. That means if I would measure not in x basis but in y basis, the other one would be like I and the other
opposite. Yes, yes. You're absolutely right. If we are talking about, say, y basis, so this is 1 and this is I. So here I will have 1 minus I. So this will be opposite state. So this phi plus state, Bell state, they have perfect correlations, like direct correlation in XZ, and basically any axis that lie in XZ plane. But for y-axis, they are perfectly anti-correlated. But it does matter whether we have correlation or anti-correlation. It's important that it's perfect. It means that we can perform measurement on the other qubits that will tell 100% of time what is the outcome of the first measurement. So this is what we have, and we have this in any basis. So no matter what type of measurement you perform on a single qubit, you will always get 50% chance of one outcome, 50% chance of the other outcome. So it's always a coin toss. If you perform quantum state tomography on this qubit, so you perform measurement in one axis, 50 by 50%, like in Z basis. That means the coordinate of this block vector is 0. You perform measurement in X basis. X coordinate is 0, Y coordinate is 0. So this is a point. You perform quantum state tomography of qubit in Bell state, you will get point at the center of the Bloch sphere, not on the surface of the Bloch sphere, but at the center. Because Bloch sphere, this vector, it properly describes only qubits which are not entangled with anything. And Bell states are maximally entangled. So quantum state tomography gives you point at the center of the Bloch sphere. So this is a state of the qubit that does not have any preferred orientation, any preferred state. So whatever you measure, no matter how you measure, you will always get 50% by 50%. Okay, so measurement of a qubit does not give us actually any information. But there is perfect correlation in any basis between state of one qubit and state of another qubit. So unmeasured qubit always end up in orthogonal states for two different outcomes of measurement. So we can always, by measuring the second qubit, we can predict or tell what would be the result, what was the result of measurement of the first qubit. So this is very unusual state, and we can say that for Bell state, so measurement of a single qubit does not give us absolutely any information. But it provides information about the other qubit. And that means that information, when we have a Bell state, information is not in the state of individual qubits. There is nothing like no information in the state of individual qubit. Any measurement is 50% one outcome, 50% other outcome. So information is not in the state of the qubit, but all the information is in correlation between qubits. Okay, so this was what makes this Bell state are so different from classical states. So you can say that when we have qubits in Bell states, that each of the qubit does not have state on its own. It's a point at the center of the Bloch sphere. No preferred direction at all. So it doesn't have its own state. So it completely lives in the correlation with the other qubit. Okay, so this is very unusual property. Let's consider another thing. What happens if we apply single qubit gates to Bell pair? So suppose I have this, again, Bell state phi plus, and I apply Z gate. Z gate flips the sign of the qubit with state 1. So if qubit is in state 0, the gate does nothing. If qubit in state 1, it flips its sign, changes plus to minus and minus to plus. I have two qubits. I can apply this Z gate either to qubit number 1 or to qubit number 0. So what will be here? What happens if I apply Z gate to this leftmost qubit? Okay, Z gate does not act on this term. It flips sign of the second term. So I will have 0, 0, minus 1, 1. It's a different state. What happens if I apply Z gate to qubit number 0? See again, it does not act on this state, on this part of superposition, but it flips sign of this term in the superposition. So this is what we have. No matter to which of the two qubits we apply Z gate, the result is the same. And you can understand this because information in Bell states is not in the qubit states. It's in the correlation between two qubits. So if you have a qubit at the center of the Bloch sphere and any gate is the rotation of the Bloch sphere, qubit does not care about this rotation. It's at the center of the sphere. Nothing happens to the qubit itself. By applying gate, you change type of correlations between two qubits. Like for phi plus states, these two qubits, like they always end up in the point, like when we measure them, in a point symmetrical with respect to y-axis, with respect to y-plane. But applying Z gate, they can be also applying some other gates. They may up in a point, say, symmetrical with respect to x-plane or z-plane and so on. So type of correlation may change. So when we apply gates to qubits in a Bell state, we do not change state of the qubit. We change type of correlations that exist between qubits. But this is correlation between two qubits. So it can be changed either acting on one qubit or by another qubit. Suppose, yes?
That gate is a single gate.
It's single qubit gate.
How do you apply to the pair of qubits?
Now, I have pair of qubits. I have pair of qubits, say, in quantum computer. I created Bell state. And then I apply this gate only to one qubit or to the other qubit. Okay. Okay, so this is what we have for Z gate. But let's see what happens for X gate. For X gate flips 0 and 1. So here I apply X gate to leftmost qubit. So here I will have 1, 0 plus 0, 1, a different state. If I apply X gate to the rightmost qubit, I will have 0, 1 plus 1, 0. So you see in one case I get 1, 0 plus 0, 1. And the other case, I had 0, 1 plus 1, 0. It's the same state. Two terms in the superposition flipped, but state stays the same. So, again, why that happens? Because Bell state has only correlation. States of individual qubits are not defined. So we apply gate, we change correlation, but we can change correlation between two qubits, either acting on either one qubit or another qubit. Suppose you have two coins. They are both heads up. They are correlated, right? You flip one coin. Now they become anti-correlated. But you can achieve the same by flipping second coin. They also become anti-correlated, because we are talking about correlations. And in Bell states, there is nothing except correlations. In classical coins, like you can distinguish them because you can look at the state of each qubit. But in Bell states, well, each qubit does not have its own state. There are only correlations. Okay, this property, again, it exists for every possible single qubit gate. So for any gate that acts on one qubit, we can find a gate that acts on the other qubit. Well, these gates are connected through this Y transformation. Why? Because this phi plus state is symmetrical with respect to Y. But it's important that whatever we do with one qubit, we can undo or like equally acting on the second qubit. That demonstrates very strong correlations that exist between two qubits in a Bell state. Okay, so this we consider it in detail properties of phi plus state. Yes?
Why is it almost the same or approximately the same? Because two qubits, like you can think like if this is Bell sphere and this is plane y equals 0. So two qubits are always like symmetric with respect to this plane. Okay, but their positions are not defined. Yes. Two qubits that are entangled as in Bell state, and they are.
Yes, and in Bell state phi plus. So phi plus, for phi plus we have this y equals 0, like a plane of symmetry. So, but that means that rotation, so two qubits are like in position symmetric with respect to reflection around this plane. So when you rotate one qubit and when you want to achieve the same action by rotating second, what you need to do? You need to take this rotation and flip it relative to the y plane. This is exactly what is done. You see, it's here, it's like this y sandwich. Okay, and we have this adjoint because we need to make mirror reflections. So this is described by adjoint. So they are not exactly the same because, again, not all directions for phi plus are equal. We have perfect correlation in x and z and perfect anti-correlations for when we perform measurements in y. So that makes this difference. Okay, but again, it's important that whatever you do with one qubit, you can undo with another one. Okay, so let's consider other states. So this state, phi plus, is not the only maximally entangled state. In fact, there are like a lot of maximally entangled states. If A0 and B0 is some basis, for example, plus 0 and 1, and A1, B1 is another basis, any other basis, you can form combination like this, and this will be maximally entangled state. For example, you can choose states that looks like this. You can form state 0 plus 1 minus. So this is a pair of orthogonal states that form basis. Well, of course, you need to have this normalization. This is a pair of orthogonal states that form a basis. So this is maximally entangled state. So here we have pair of orthogonal states, and here we have pair of orthogonal states, and they have equal weight. That's all. That's the maximally entangled state of two qubits, and you can form like infinitely many of such states. So there are 4 states which are often used and have special names, and this is a state that are called Bell states. Like in general, if we are talking about one Bell state, that's usually phi plus. But Bell states in general is one of these 4 classes. Yes, please.
You say that we can make maximally entangled states by any 2 sets of orthogonal bases. They have to be, the orthogonal bases have to be linearly independent, I guess.
Yeah, we can choose bases for one qubit and bases for another qubit independently. Yeah. So that's like yeah, because in principle these 2 qubits, they that form Bell pair, they do not necessarily have to have the same physical nature. Also what is interesting, like for example, we may have one superconducting qubit and one photon, and then can form Bell pair. And then the notion of the same basis, it's not physical, because, okay, for superconducting qubit, by basis 0 is the ground state, 1 is the first excited state, but for photon 0 is horizontal polarization, 1 is vertical polarization. So there are no the same basis for two qubits. And yeah, we can form Bell states of qubits of different nature. We can form Bell state of magnon and superconducting qubit, and this is something that was very recently achieved. So one of research papers is exactly about this, on Bell state. Okay, so this is a family of 4 Bell states. So phi plus, phi minus, psi plus, and psi minus. So they are all formed like 2 terms in computational basis. So how to understand them? So phi states, for states phi, we combine 0, 0, and 1, 1. So here I have 0, 0, 1, 1, and here I have 0, 0, 1, 1. So these are the states in which 2 qubits are in the same state. So you can say that they have even parity. Either 2 qubits 0 or 2 qubits 1. For psi states, I have odd parity of configuration, 0, 1, and 1, 0. Okay, states with superscript plus, they have sign plus between these 2 parts of superposition. States with sign minus have sign minus. So it's actually very simple. Phi is even parity, the same as phi plus. Psi odd parity. Plus, you put here sign plus, minus, you put here sign minus. All these 4 Bell states, they share the same properties as phi plus, and basically these are common properties for all maximally entangled states. So probability of outcome of single qubit measurement is always 50%, no matter what axis we are measuring. Post-measurement states of 2 qubits are perfectly correlated, but well, these correlations are different for different qubits. So like phi plus, they are symmetric with respect to y plane. For other states, the symmetries is different. And any single qubit transformation, well, we can achieve it by either acting upon 1 qubit or another qubit. Now, these 4 states, we can easily transform from one state to another. So if we generated one state, we can transform to other Bell states by using single qubit gates. So it's very easily. So for example, when we apply Z-gate to state phi plus, and it does matter whether we apply it to 1 qubit or another qubit, we end with state phi minus. Because Z-gate, it flips signs. It flips signs of state 1, so it changes from plus to minus. So Z-gate, generally, it swaps plus and minus Bell states. So you have state psi plus, you apply Z-gate, no matter to which qubit, you get psi minus. Similarly, X-gate flips between phi and psi, because X-gate, it changes one of the qubit from 0 to 1 or from 1 to 0, so it changes parity of the state. So overall, we have this very nice picture. We have these 4 states, and we can go from plus to minus by Z, applying Z-gate, and from phi to psi or back by applying X-gate. So it's very simple. Z-gate is responsible for sign, while X-gate is responsible for parity. Now why we consider why there are 4 Bell states and not more than 4 Bell states? Because 4 is the size of the basis for 2 qubits. Like usually we are using computational basis to describe qubits 0, 0, 0, 1, 1, 0, 1, 1. There are 4 states that form a basis. But you can use these Bell states as a basis. So they form basis for 2 qubit states. And this is absolutely normal orthogonal basis. So we can write any qubit in this basis like this, any 2 qubit states in this basis. So this is some 2 qubit states. We can expand it over Bell states as usual, and we can find each of this expansion coefficient a scalar product of the state we expand with corresponding Bell state. So this is basis, and sometimes in some protocols it is convenient when we have 2 qubits, it's convenient to think about them in this basis. Okay. So Bell states, as I already said, they are very important. So there are a lot of quantum algorithms that require them and would not be possible without them. Okay. And also what is important about Bell states, to prepare Bell state, 2 qubits has to interact. But we can prepare them locally, and then we can send some qubits somewhere far. Correlation exists. So these correlations are non-local. So this is entanglement. Entanglement is non-local. You create entangled state between your qubit in your superconducting computer and photon. You send photon to some quantum server that received it, and this is the way how you can send information between your computer and the server using Bell states and quantum teleportation, something that we'll study in next week. Okay, so the question is, how can we generate Bell state? So we need to apply some quantum gate that will work on both qubits. So these qubits will interact. So we need to apply entangling gate. So entangling gate is a special notion in quantum computing. This is a gate capable of producing entanglement. And development of efficient entangling gates, well, it's important topic in quantum computing. And here, if we can use full power magnons, so magnons are capable in principle to entangle 100 of qubits at once. So to create entangled state of 100 of qubits, that would be very good. But okay, so to generate Bell state, just one Bell state, we need to have some entangling gates. Usually, most commonly using gate is a control node or CNOT gate. So right now, we'll a little bit switch gears and talk about this gate. So we'll talk more about multi-qubit gates in CNOT gate next lecture, but now just a brief introduction to understand how we can detect, how we can generate, and how we can measure Bell states. So control node gate. I already showed this gate in some examples with Kirk on last seminar. So control node gate, CNOT, and also it is called control X or CX. Okay, so this is de facto the only standard 2-qubit gate in modern in quantum computing. So all other gates can be derived from it. So this is the notation for this gate. So this is notation for X gate. This dot indicates control. So execution of this gate is controlled by this qubit. So this qubit is called control qubit. It controls whether the gate is applied or not. This qubit is called target qubit. So this is the qubit to which X is applied or not, depending on this state. So this is how we write it in algebraic notation. CNOT, control comes first, target comes after that. So the qubit which stays near CNOT is the control qubit. So what is the action of CNOT? So in computational basis, so this is where we can understand everything similar to standard Boolean algebra. So if state of control qubit is 0, this circuit doesn't do anything. But if state of control qubit is 1, it applies X gate to the target qubit. So this is control NOT gate. You apply NOT or X, NOT and X is the same. You apply NOT if your control is 1. So it's very simple. So we can write action of this gate in computational basis. So if 2 qubits are 0, well, the result is 0. Here, control qubit is 0, well, the result is the same. So in computational basis, you see red is the control qubit. It does not change its state. Well, it just controls execution of this X gate. When control qubit is 0, state of target qubit stays the same. When control qubit is 1, state of target qubit flips. From 0 becomes 1, from 1 becomes 0. Okay, we can write simple algebraic formula. So this is how we can write this action. So control qubit stays the same, and to the target qubit, a target qubit is XORed. So this is XOR operation or addition modulo 2 in Boolean algebra. Target qubit is XORed with control 1. So if control qubit is 0, here I have target, well, XOR is basically like plus addition, but modulo 2. So target plus 0, just target. If control is 1, here I have target plus 1. When we have only 0 and 1, then target plus 1 is the same as apply and not operation. So this formula is very useful when we have a circuit with several C nodes, or several of these operators, or maybe some other similar operators like control node. So node which is controlled by the state of 2 qubit. So this is it's very convenient to use this formula to understand what this circuit does. I think in the second homework there is one problem exactly for this. There are like 7 or 8 control node gates, but you use this formula, you can easily understand what it does. We can write control node in matrix form. So it has block diagonal form, and this block, which is identity matrix, it tells what happens to target qubit when control is 0. So nothing happens. So this is just identity matrix. This tells what happens to target when control is 1. This is the matrix for X. So we can also write it in nice form like this. Block matrix form. So it's block diagonal, here is nothing, here is X. So this is the only form that it can be easily understand. A human can easily understand, because this is already 4x4, it's too much. Now, in most cases, when we have a quantum program and we want to write it as some like algebraic formula, or even if we want to write a code in Qiskit to realize this quantum circuit, we need to indicate which of the qubits are control and which are target. Because usually we have more than 2 qubits, we have several qubits. So when we write C naught, how do we show to which qubit it's applied? Well, using subscripts. So first subscript is control, second subscript is target. When we write this control node operation in Qiskit, so name is CX. Qiskit use short versions, short names for all gates. So instead of node we have X. Well, it's synonym, so instead of C node we have CX. So this is control, this is target. So control comes first. And there is a difference. So this is C node with control on qubit number 1, because this is qubit 0. We start from top and start from 0, 0, 1. So this is C node 1, 0. This C node in all other directions, C node 0, 1. They are different. They have different action. Okay, so here, like we will consider more interesting thing with C naught, and using C naught and other gates. Sometimes you can achieve a fact which seems absolutely impossible. Like, okay, but for now we can consider just very simple circuit with C naught. So let's consider this circuit. So if we start with 0, 0 state, here we have Hadamard gate, and here I have control node with control on this
qubit to which I apply Hadamard gate. Let us find final state generated by this circuit. How to do it? Like we will proceed slowly, like from this point to this, and we'll calculate like at every step, we'll calculate what is the state will be. So the initial state here is 0, 0. Then after Hadamard gate, I apply Hadamard gate to this qubit number 0. Hadamard gate switches 0 state into state plus. And state plus is 0 plus 1 divided by square root of 2. So it's a combination of 0 and 1. For simplicity, I can like write this tensor product of 0 and plus state. I can expand it like this. I have 0, 0. This is this term. And I have 0, 1 state. 0, 1. So this is what I have after Hadamard gate. Now I apply control NOT gate. So control is this qubit number 0. What happens to, and gate is linear, so we know how control NOT acts in computational basis, but here I have superposition of computational states. Any quantum gate is linear. We can consider like its action term by term. So what control NOT does to this term? Well, it does nothing. Because, well, control qubit is 0, so it does nothing. But here, control qubit is 1. So it flips target qubit. So the result after application of control NOT is superposition of 0, 0 term that come from this and 1, 1 that come from this. And this is exactly state phi plus, Bell state phi plus. So this very simple circuit, like we can call it Bell gate, sometimes it's called like that, but it's like not official name. So we can call this circuit simple circuit Bell gate. It appears very often in quantum programs, so you can, when you look at many algorithm, you see it very often. So this very simple circuit produces Bell state phi plus. So this is how we can generate this Bell state. Okay, so let's consider the generation of Bell states in more detail. So we already know that Bell state phi plus is produced by this Bell gate. And I will switch to Kirk to demonstrate how we can do this, how we can measure this. So this is, this Bell gate. Okay, so you see here, in this Kirk shows like for each qubit, it automatically shows Bell sphere, Bloch sphere. So we see where this point that corresponds to qubit on Bloch sphere is. It's at the center of the Bloch sphere. So for comparison, if I remove control condition, here it is normal vector. But once, because this state is not entangled state. So we have Bloch vector of length 1 point at the surface of Bloch sphere. But here I have Bell state. So point, it shows a point at the center of the Bloch sphere. This is result of single qubit measurement in Z basis, 50%. If I measure in different bases, 50%, 50%, 50%, 50%, no matter what I do, it's always 50%. Because I measure one qubit and that's all. So how can we tell that this is Bell state? We can measure 2 qubits at once. So when we are using this measurement probe, we can expand it over 2 qubits. And then that corresponds to it will show us result of 2 simultaneous, of measurement of 2 qubits simultaneously.
So, and even we measure 2 qubits at the same time, there are 4 possible outcomes, 0, 0, 0, 1, 1, 0, 1, 1, right? So here I have 4 possible outcomes. You see, only 2 outcomes are possible for this state. So here is this a chance of 0, 0, 50%. There are no combinations 0, 1, and 1, 0. And this is chance of 1, 1. Okay. So how we can see in simulations that we have Bell state? Well, this is a good indication that we have only 2 possibilities out of 4, and they have 50% each possibility. We can also look at the amplitude, as amplitudes can also be extended like so here. So this block shows a depiction of amplitude of expansion of state. So if I have quantum state, 2-qubit state, psi, I can expand it in computational basis like this, where each coefficient is a complex coefficient, so it has amplitude and phase. So there are 4 complex coefficients. So this block, it shows 4 of this complex coefficient, like a radius of this field region is correspond to absolute value of this coefficient, and this line corresponds to phase. So we can hover over this and see amplitude of 0, 0. So this is amplitude of this term. So so how this amplitude looks as a complex number, magnitude, phase. So for Bell states, this pattern is diagonal pattern like this. Diagonal pattern. Well, I told you that we can switch from one Bell state to another Bell state by applying single qubit gates. So let's do it. So this is one way how we can generate other Bell states. So this simple Bell gate, it gives us phi plus state. We can generate other Bell states by applying single qubit gates to this state. For example, when I apply Z gate, I obtain state which is phi minus. Phi minus, it still has the same 2 components, 0, 0, and 1, 1. 0, 0, and 1, 1. But phase between them changes. So here I have the same phase. For phi minus, the same will be, or the phase will be opposite. This is what happens when I put Z gate on one of the qubits. You see 50-50, it stays the same. What changes is just the phase of this component flipped. So this component stays the same. 0 of 7 is 1 over square root of 2. Also, we often see it with such amplitude display. And here is sign is changed. What happens if I apply Z gate to the other qubit? Nothing changes, you see? Nothing changes. It does matter to which qubit we apply gate. The result is the same. We transform from plus, phi plus state to phi minus. When I apply X gate, single qubit X gate, I switch from phi states to psi states. So, and in psi states, so in phi states, I have 50% of these 2 possibilities, which is 0, 0, and 1, 1. And here I have 50% of 0, 1, and 1, 0. But still it's 50%. Only 4 of these 4 possibilities for simultaneous measurement is possible. And here we can see these amplitudes. Okay, I can apply X gate to one qubit and Z gate to another. So what happens? X gate switches from phi to psi, so from even parity to odd parity, and Z flips signs. So here is the sign. So this is how we can generate Bell states. There is another method how we can generate this state. So here, my circuit starts with 0, 0. This is how we usually start, like the initial state of all qubits at the beginning of quantum program, 0, 0. But let's see what happens if I start with a different state. So if I start with state 1, 0, so instead of 0 here, I will have 1. See what happens? This phase flipped. So if instead of 0 here, I start with 1, this phase flipped. Why that happens? Because when we apply Hadamard gate to minus state, we get not 0 plus 1, we get 0 minus 1. So everything with this 1 will have sign minus. So if I apply Bell gates to state where here I have 1, well, I will have state with corresponding minus. Similarly, well, if I start with 1 here, instead of phi state, I will generate psi state. Why? Because, well, this is, when I start with 1 here, is the same as I apply additional X gate. Okay. So here I start with state 1, 1. So this Bell gate generates state psi minus. Minus because 1 here, psi because 1 here. So this is there is another way to generate these states using different initial conditions. Okay, so again it's illustrated here like this. So 0, 0, phi plus. This qubit controls whether we will have sign plus or minus. Okay, here is a summary of this. Bell's gate fed by 4 different computational states. If we start with 4 different computational states, we will generate 4 different Bell states. This qubit, 0, 1 here controls plus minus. 0, 1 here controls phi or minus phi. Okay, and yeah, this is like the first method. Like we can also apply the gate. But the fact that Bell gate transforms, so what we see here? We see here that we start with 4 different computational basis states and end up with 4 different Bell states. So this gate performs transformation from computational basis to Bell basis. So Bell gate transforms from computational basis to Bell basis. So we can write even based on this, we can write direct notations for this Bell gate without calculating, without any calculation. So it takes state 0, 0, transforms to phi plus, state 0, 1 to phi minus, and so on. So we can consider Bell gate as transformation, as a gate that describes transformation of basis from computational to Bell basis. And respectively, a joint gate, like, and how to create a joint when we write quantum program. A joint is like we need to reverse order of gates and apply and adjoint each of the gate. Well, C0 or Cx, well, X and Hadamard gate are self-adjoint because they are involutions of applying this gate twice gives the same as identity gate. So inverse to C0 and inverse to Hadamard gates are the same. So to get a joint of Bell gate, we simply need to put these 2 gates in opposite order. So first C0 and then Hadamard gate. And this gate performs inverse transformation from from Bell basis to computational basis. Okay. Now, how can we measure Bell states? Suppose I gave you two qubits in some Bell state. You know that this is one of the 4 Bell states, but you don't know which Bell state. How can you determine which state it is?
To convert to states and to measure statistics.
You have only one state. I will not give you more. I will give you only one pair of qubits, and you have to determine it. Which Bell state you have. Okay, suppose I give you one pair of qubits and I tell you, these qubits are in one of the 4 computational basis states. So they're either 0, 0, 0, 1, 1, 0, 1, 1. But you don't know which. Can you determine which qubits you have? Like, can you perform measurements that it will tell you? This is just usual measurement. Okay. Now, so if you have like usual 0, 0, 0, 1, 1, 0, 1, 1 states, like you just measure them. Like you have tools in quantum computers that allows you to measure, distinguish between 0 and 1. Directly built in, like it's called measure in Qiskit. Okay, so we can directly measure this qubit, and you can tell just from one copy of this pair. Well, assuming that everything works 100% cases and so on, no errors. But now I gave you Bell pair. You don't have in your quantum computer, you don't have possibility to measure Bell pair. You can measure only in computational basis. So what should you do?
Inverted C0 and measure.
What do we need to do? Right, we need to transform from Bell basis to computational basis. We need to perform, okay, we can measure only in computational basis, but when we want to distinguish one of 4 Bell states, what we need to do? We want to perform measurement in Bell basis, right? To distinguish between Bell states. That means measurement in Bell basis. We cannot do it directly. What we need to do? We need to transform coordinate from Bell basis to computational basis. This is exactly the same as part of assignment in lab number 1. So, because to perform quantum state tomography, you need to measure X component of qubit, to measure qubit in X basis. You cannot do that directly. So what you need to do, you need to transform basis, apply Hadamard gate, and also for Y basis as well. So here it's a little bit more complicated because we are talking about 2 qubits, but the idea is the same. Like we want to measure in this basis, we want to distinguish between certain states. That means measure in basis of these states. We cannot do it directly, so we need to apply gates that will perform transformation of coordinates. And here is this gate. Okay, so such measurements, they are very important, and there is like special standard name. This is called Bell measurement. So you can write in your paper. So we have these 2 qubits, and we perform Bell measurements on them. So this is like a standard thing. Okay, so measurement is just inverse of generation. So to generate, well, we have here 0, 1, we put this, and we get phi of psi plus minus. To measure Bell state, we reverse this circuit, and then if input is phi of psi plus minus, output is like 0 and 1. So this qubit which has Hadamard gate is responsible for plus or minus. This qubit which does not have Hadamard gate is responsible for phi of psi. So let's
see example. So here I generated Bell state. And then I will perform measurement of this Bell state. And this 2-qubit measurement shows result. So this is the measurement part. So outcome here, you see, if I measure Bell state, I get two possibilities because there is superposition of two computational states. This collapses it back to the state. So this is 0, 0, 0, 1, 1, 0, 1, 1. So it's 1, 1. That means which state? Well, this one means state minus. This one means state psi. Well, so here I have state psi minus. Because I started with 1, 1. So generated psi minus. So basically here I have 1, 1 and here I have 1, 1. If I start, okay, go on.
After you do this inverse Bell state thing, they are still entangled afterwards?
No.
Oh, they are?
No, yes, they are not. So if, okay, this is a very good question. If here I have Bell state, like particular Bell state, they will not be entangled. So this they will disentangle any Bell state. But for example, if here instead of Bell state I have something else, like this. Now, so here, so at this point it's not Bell state, right? It's superposition of Bell states, right? Because Bell states is a basis. So whatever I have here, I can describe as superposition of the Bell states. So after Bell state gate, I will have superposition of different computational states, which may be entangled. Well, depending on details. But if I started with a nice one Bell state, then after Bell measurement, they will not be entangled. Okay, so here I start with 0, 0. I perform Bell measurement, I have 0, 0. Okay, if I put, say, X gate, I put X gate here, so this A gate changes phi plus into psi plus. So, and here it moves from this phi plus to psi plus. So I can say that this is psi plus. Okay, and now you see, say, if I put, say, Z, so now I have psi and I have minus. So state psi minus. So here, this I measure the state 1, 1, which means psi minus. Now, here I have Hadamard gate on the top line, and here I have Hadamard gate on the top line. But in Bell states, both qubits are completely equivalent. So I can actually, this measurement, I can do them like this. I can flip this gate. Still it performs measurement. So this is ZZ. Okay, now it is here I have state phi minus, so phi plus from simple Bell gate, this switch sign. So this is psi minus, and here I have state 1, 0. So 1 here is the bottom qubit. It responds for this configuration of Bell measurement. It describes sign. Okay. If I remove here, go back to phi plus, I have phi plus
So you see, I can measure one way or another way. Okay, so this is how we perform Bell measurement, and it's also like this Bell measurement technique, it again illustrates this idea. So the gate, they have like, we can look at quantum gates from two different points of view. So we can look at them like these are some actions that we perform on state, or as transformation of coordinates. And the second picture will be important next lecture because there will be several examples of that. Okay, so these are the examples. Okay, and yeah, like you can perform these measurements, things like that. Okay, that will be all for today. In my slides that I put on Moodle, there also will be additional material on superdense coding. I think also with some IBM program test of this superdense coding, so please also look at that because it's also very interesting, again demonstrates new possibilities that exist in quantum physics. Because one of important things, like if you are going to do quantum science, you have to think differently. You have to think like this is not gate, this is transformation of basis. That you will not send information, you will teleport it, or something like that. Okay, so there are quantum computing and quantum physics, they provide a lot of opportunities which do not exist in classical physics. And if you approach like quantum research exactly as you approach classical research, there will be some experiments that you may not even think of. So one of the important things is to try to look at this algorithm, and not just the algorithm itself, but slightly beyond what they represent, type of using quantum resources. Like gate is a gate, but it's also transformation of coordinates. It can be whatever we want. Okay. So, and superdense coding shows, again, like very interesting application of quantum computing. Well, it's not practical, but it illustrates like, interesting possibility. Like, you know that to measure one qubit, that each qubit can be measured only once. After that, it collapses and there is no point measuring them again. So, to send n bits of information, I have to send you n qubits, because you can measure each qubit only once. Superdense coding shows the possibility how I can send you 2 bits of information by sending only 1 qubit. And of course it uses entanglement. And of course it uses Bell's path. And it uses everything we studied today. So please look at this additional slide. That will be all for today.